but we can catch up. There's kind of room at the end of the course for this matter. I think it's more important that we go through it slowly and properly, and because I think it's like one of the fundamental aspects of this course is kind of what we're going to get to today. And the stuff that I've been promising for weeks and weeks before this, including the public holidays, is the fact that eigen decomposition and matrix decomposition falls out if you understand how bases work. And so hopefully that becomes clear today. And if that's the only thing you take away from today's lecture, or at least part 2's lecture, it's that. So if you remember, we spoke about multiplicity last time. So there's the geometric multiplicity, which we're going to chat about today, but there was algebraic multiplicity, which is how many times a particular eigenvalue shows up in an eigen decomposition, right? So if you get lambda is equal to 2 squared, or lambda minus 2 squared in your characteristic polynomial, that squared means the algebraic multiplicity for that eigenvalue is 2. All right, so if it's power of 3 or 4 or whatever. Okay, this is the geometric multiplicity. Okay, so this says for a given eigenvalue lambda I of a square matrix A, then the geometric multiplicity of the lambda is the number of linearly independent eigenvectors now associated with the lambda i's. All right, so it's now no longer got to do with the eigenvalues, it's the eigenvectors that we're trying to describe with this value. Okay, what it ultimately is the dimensionality of the eigenspace defined by a particular eigenvalue. Okay, so the number of dimensions that get stretched by a value of 2, if your eigenvalue is 2, for example. Okay, so specific eigenvalues geometric multiplicity must be at least 1, because every eigenvalue has at least one associated eigenvector, but it can have multiple, obviously. And then an eigenvalue's geometric multiplicity cannot exceed its algebraic multiplicity, but it can be lower. And this is the key point, right? You can get the eigenvalue 2 showing up multiple times, so your algebraic multiplicity can be 2, let's say, if you know it's lambda minus 2 squared in your characteristic polynomial. So lambda minus 2 squared is showing up in your characteristic polynomial. That will give you an algebraic multiplicity, but it's possible that we only get one eigenvector associated when we solve for that. In that case, you have an algebraic multiplicity of 2 and a geometric multiplicity of 1. Okay, and the geometric multiplicity is always related to a particular eigenvalue. All right. So since we can look at an example of this, so consider this matrix A. Since it's an upper triangle, we know that its diagonal elements will just be its eigenvalues. Okay, and so lambda 1 equals lambda 2, which is 2. All right. However, when you go and solve for the eigen decomposition in this case, what you'll end up with is finding that this is the only eigenvector. So in this case, the geometric or algebraic multiplicity of the eigenvalue 2 is 2, right? Because it's lambda 1 and lambda 2. But the geometric multiplicity is only 1.
Is that because that's how many vectors there are?
Yes.
Okay, so like if it was like x1, 1, 0, and then I guess x2, like 0, 1. Then, okay.
Yeah, then it would be in geometric multiplicity 2.
Okay. And it can be equal then, like it's not, is it strictly because the definition before was you said it cannot exceed it?
Yeah, so you're never going to get a case where this is now 2 and you have 3 vectors here.
But can you have 2 though?
Yes.
Okay, so it can be equal.
Yes, most cases will be equal. All right. The cases when it's not equal is when you have a low rank or a singular matrix. Okay. We'll come to that in a second. But to begin with, I think it's helpful to have a little bit of intuition for what is going on in the eigen decomposition. And this very much follows my box example that I've been doing for like weeks. But it's now a little bit more formal and in the slides. So it's kind of at least a more concrete way of understanding it. So in order to add a bit more of a tangible feel to the implications of things like determinant, eigenvector, eigenvalues, we consider a couple of different linear mappings. To begin with, consider A1, which is just a diagonal matrix. In this case, you can read off the eigenvalues off the diagonal. All right. And then the corresponding eigenvectors are the canonical basis. All right. So you would decompose this to be 1, 0, 0, 1, a half, 2, 0, 0, and then 1, 0, 0, 1 again. Okay, in that case, those are your eigenvectors, obviously, and then those are your eigenvalues. So you can really see that this was essentially in an eigen kind of basis. Okay, in this case, it's the canonical basis. So if we interpret what it is doing, when we apply this matrix to data, right? So if we take all of these data points here, here, and here, and we apply A to it, what happens to the space? Well, in the one direction, so in the y direction, it is being stretched. And it is now twice as long as it was before, right? In the other direction, it is being compressed, so multiplied by a half. So it's going to be half the length as it was. Okay, so initially that was 1 unit long, that's now half a unit long. That was 1 unit long, that's now 2 units long. Okay, that's the intuition for what this is doing, and it's just because it's on the diagonal, it's just stretching in the individual dimensions. Okay, what's interesting is that the determinant, though, of this matrix is just the product of the diagonals, which is 1. And so what does that mean? That means that the volume, not volume, 2D, it's the area has not changed. Okay, this still occupies one area, one whatever, centimeters squared or whatever, call it whatever you want. Okay, in this case, it was a 1 by 1 square, which means that the area was 1. In this case, it's a 2 by a half rectangle, but still area is 1. Okay, looking at a shear matrix. In this case, the determinant is still 1. Okay, so the shear mappings are area preserving. All right, and so shear mapping just says that if I have elements along x and y, they're going to stay the same, but also I'm going to move it over a half unit to the right if the other variable is active. Okay, so for example, if I was in like a y1 space, then I'm going to shift over to the right the positive half step, which is why you end up moving to the right. Okay, if you're off in this y dimension, then your next x element moves to the right a little bit. Okay, so that's just how a shear matrix works, but it preserves your map, or it preserves your area, and ultimately your eigenvectors themselves stay 1. All right, so there's no stretching happening. It's just a translation, a movement of the data points that say if my data point started in the positive y-axis, it's now going to move into the positive x-axis a little bit. And if it started in the negative y-axis, the new data point will move into the negative x-axis. Okay. Rotation matrices, we went through these. This is a rotation by pi over 6 radians. This is a counterclockwise mapping and has only complex eigenvalues. And so in this case, the determinant is still 1. So it's area preserving, but now obviously you've rotated your set. And the intuition, kind of, if you want to think at least a little bit for where the imaginary numbers come from, this restriction that you have on your eigenbasis doesn't make sense. Okay, in the sense that a rotation isn't actually a particular, it can't be thought of as a linear translation in the kind of standard sense. And so what we have to do is we don't have the flexibility to do that. You have to extend into the imaginary dimension so that you then have a dimension to rotate around. Okay, and then you collapse back down, and that's your eigenvalue. All right, I know it's a bit of a hand-wavy way of thinking about it. That is essentially why you get now imaginary numbers coming out of it. Is because you haven't actually stretched in the real plane. What you've done is you've stretched into an imaginary plane so that you have something to rotate around and then collapsed back down. And so that's now why your data looks like that. But then your eigenvalues are imaginary. They aren't actually particularly sensical in that sense. Okay. What we kind of deal with in this class, I can promise you, you won't get imaginary eigenvalues in a test. Okay, all right, then looking at this matrix here, so in this case it's a little bit more complicated, but here the eigenvalues are lambda1 is equal to 0 and lambda2 is equal to 2, all right? So to say to you guys, what's the algebraic multiplicity of 2?
2, 1.
Okay, it only appears once, right? There's only one eigenvalue with the value 2, so it's 1, all right? And then the corresponding eigenvectors are 1, 1, and minus 1, 1. The determinant in this case, though, is 0. Okay, so what does V1 equal 1, 1 tell us if the eigenvalue is 0? Put differently, what does it mean that the determinant is 0 when we started in a 2D space? Let's give someone else a shot. Yeah.
Space reduced.
Reduced. Need a little bit more precise? You're correct. You know what you want to say. You can see it in the image as well. If you want to just describe what these images are doing. Exactly. You've lost a dimension. You took something that was square, it had area, and it now lies on a line. Okay? You've now lost a degree of freedom. Your data can only sit on a line after you've multiplied it by A. Okay? You've taken something that had area, and now it has no area. All right. Nicely done. And so this vector v1 is equal to 1, 1 tells you which dimension got lost. It tells you that any data point lying in the direction of 1, 1 will now land on that line. Okay? Anything, any variance in that direction can no longer be described after I've applied by A. What is this called? We've spoken a lot about this. There's a theorem named after it. We even said it's the most important theorem, and I know for a fact it's the one you all are scared it's going to come up in your exam. Yeah. Okay, so what's this direction? What's 1, 1? Which of those words does 1, 1 describe?
That's the image.
It's the null space. It's the part of your input here that gets mapped to 0 after I apply A. All right, your null space is what gets left behind. Okay, and the rank nullity theorem said that the dimension of my data after a mapping plus the amount of dimensions that got left behind, the dimensions in my null space, must be equal to the original dimensional space I was in. So original dimensional space, we have a square, so it's 2-dimension. Afterwards, I'm in a 1-dimensional line, and my null space was that 1 dimension there that got lost. So the dimension that got lost plus the dimension of my line gives me the original dimension, which is the square. Rank nullity theorem. Yes.
When we talk about like the image and kernel, that also does like a similar mapping, right? Where it removes like when you have the one like line that's orthogonal to the line.
Yes.
That's the is the reason, like I guess it's different is because I mean maybe there's many points here on why is it different to like the image or kernel?
Well, I mean, so this is the image of A, and then this is the kernel of A, right? They operate in the 2 different spaces.
So one is the kernel, but also the null space.
Yeah, kernel and null space are the same thing.
Okay.
Yeah. Sorry, those are the exact same thing, just with 2 different names. So that's a good point. I should be more careful about that. The image then is a different thing. Okay. And then lastly, consider a shear and stretch mapping. In this case, the determinant is 0.5. And so the area is scaled by 0.5. It stretches space along the red vector by a factor of 1.5 and compresses it along the blue vector by a factor of 0.2. And so ultimately you have a lower area. Right, you can have a look at that example. Okay, so then theorem 4.12 says that the eigenvectors of A with n distinct eigenvalues are all linearly independent. Okay, and so this is the thing, one thing that matters. Yes.
Just going back to what so the null space and kernel, they're the same thing, but the image is also interchangeably formed with the column space. Is that correct? Or
No. No, because the column space of A are these things, right? So that's like you're going to build a linear combination of your columns. But if you have columns that are linearly dependent, you can then cancel them out. And so your image falls away.
so in that case, like when they are linearly dependent, then whatever is like completely left behind.
Yes. If your columns are linearly independent, then they're your image, yes.
Okay, that makes a lot of sense.
Okay.
I mean, row space is unrelated to both of them.
Yeah, I wouldn't think in terms of rows. In terms of like constructing new spaces. Rows have their own meaning. Yeah. Yeah, and that's because when we do these matrix multiplications, it's always, like this. It's x1, x2, right? So in that case, you're doing that times by x1 plus that times by x2. You're always constructing the x1s and x2 as your linear combinations of each of the columns. I always think about row spaces. It's in an earlier set of slides, but the row space to me is something that defines like concentric circles, or like, these, it's the number of vectors that if I then take, let's say, that row and multiply it by x1, x2, right? It's now how many of these lines my blue vector intersects in that direction. So rows to me are a measure of distance. Okay, and that's why like you can use them as a metric space to define like an inner product. So yeah, I think there are different things. Rows are called covectors, and they're taken a very different geometric interpretation. That is in, I think, lecture 4. We talk about that. Cool. Everyone happy? Cool. So theorem 4.12. So eigenvectors with n distinct eigenvalues are linearly independent. This theorem means that the eigenvectors of a matrix with n distinct eigenvalues forms a basis of Rn. In general, the eigenvectors which have different eigenvalues are going to be orthogonal. Okay. The only time you're going to get non-orthogonal eigenvectors is when they share an eigenvalue. In other words, when that eigenvalue has a higher algebraic multiplicity. Okay. This helps us define defective matrices. So if A is a square matrix and it is defective if it possesses fewer than n linearly independent eigenvectors. Okay. So if geometric multiplicity is lower than algebraic multiplicity, you have a defective matrix. I know the multiplicities idea is subtle and annoying. What I would say is that, like, I think it's important that we define it, but in general, I think if you understand more things like column spaces being linearly dependent, those sorts of things, I find that to be a more useful way of going about it. That's less definitions heavy. Okay, but note that a defective matrix does not necessarily require indistinct eigenvalues, but it does require that the eigenvectors form a basis of Rn. Okay. So again, if geometric multiplicity matches algebraic multiplicity, even if algebraic multiplicity is greater than 1, if you have that many distinct vectors for that space, then you're still fine. Okay, so it doesn't go both ways. If a matrix has geometric multiplicity less than the corresponding algebraic multiplicity, then the matrix is defective, and then a defective matrix cannot have n distinct eigenvalues. All right, this follows from 4.12, but it also follows more from this example. Right? We got a 0 there. And so it was defective. There was a dimension that was lost, was mapped to 0 by my matrix A. Okay? And so that's a defective matrix. Why is it defective? Because if I give you this point over here, or let's take one not being silly. If I take this point here and I ask you to put it back into the original space, where do we put it? It can go anywhere there. How do I know which spot? And that's the whole point. That's why it's non-invertible. It's defective because I've lost information. Whatever got mapped to 0 cannot be recovered now. Okay. All right, but importantly, positive semi-definite matrices. So given a matrix that is n by n, so not necessarily square, we can always obtain a symmetric positive definite matrix S by multiplying it with itself. This is very, very similar to squaring a matrix. Like once you square something, it's now positive, whether or not it started as a negative value. Same sort of intuition. Okay. If the rank of the original matrix is n, then the S matrix will be symmetric positive definite. All right. So in the original definition, it's semi-definite, but in this case, it's positive definite. So we'll look at that why now, and also just to note that I reminded you what these definitions are. So symmetric means that it's equal to its own transpose. Positive definite means that for any non-zero x, if I use S as a metric, it'll give me a non-zero number. Yeah. Yep.
Sorry, the one with this one. So the algebraic multiplicity in this case is like in total is 2 because there's two unique eigenvalues, or is it one?
I think counting zero as an eigenvalue is ridiculous.
Yeah. So it is one.
Yeah.
And then.
Well, again, your algebraic multiplicity is always going to be relative to an eigenvalue. So I'm going to say, what's your algebraic multiplicity of 2? So if I am a stupid question, I was asked her and I say, what's the algebraic multiplicity of 0? Then you roll your eyes at me and you say 1. And then you tell me I'm an idiot. But like in general, I'm going to tell you which eigenvalue am I asking the geometric or algebraic multiplicity for.
So for this example here, where we have L1 equals 0, L2 equals 2, then we have the geometric multiplicity as 2, because there's the two distinct vectors, or is that wrong? There's V1 and V2.
Okay, so geometric multiplicity cannot be higher than the algebraic multiplicity.
Yeah.
So it's 1 for each of them. And so the geometric multiplicity of 2 is only that vector. Yeah, exactly. V1 is related to there. You can see that's why V1 is sitting at that origin. Yeah, no worries. Okay. So motivation for why this is true. So let's consider the symmetry property. So if S is equal to A transposed A, then it means that if I want to consider the S transpose, is it equal, right? So to begin with, we're going to transpose this, okay? And if you FOIL it all out and do a whole bunch of like kind of absurdly unnecessary transposings, what you ultimately end up with is saying that S transposed is equal to that, okay? But we know that there's this property of A, B transposed is equal to B transposed A transposed, all right? Which is essentially what they're applying on that line above, plus a whole bunch of like unnecessary transposes. I don't think this is necessary to do that, but anyway, it's in the slides. Well, this way, this is a very easy proof and not one that will be asked. But all you would have to essentially say is S transposed is equal to A transposed A transposed, which is equal to A transposed A. Or if you want to be more precise, A transposed transposed. Okay, so you've taken that element and transposed it, and you've taken that element, transposed it, and you very clearly reversed the order. And so in that case, A transposed A, which is equal to S. Okay, so that's now shows that it is symmetric. Okay, and then the positive definite case I think is a little bit more interesting. So what you're going to do is you're going to say let X be an element of the reals excluding 0, and then observe that if we now use that as the metric to do the inner product, what happens? Well, S gets substituted in with A transposed A, which then means we can group X transposed A transposed together and AX on either side. Those are essentially two new vectors, and then using that same property of A, B transposed is equal to B transposed A transposed, we now use it in reverse on that bit there, okay? And so what that does is that then that says that it's AX, come on. We ultimately get AX transposed, right? And so now in this case, you can see that those are two new vectors with their own inner product, and as a result, we know that that's going to be positive or 0. What is the case when that gives you 0?
Is it when you have like a null space?
Correct. Why? What happens?
Yeah.
Correct. X can sit in the null space. And then as you can see here at the bottom, it says that that would require your rank to be lower than the dimensions you're embedded in, obviously, so that you have a null space. If your rank is equal to n and you're in Rn, there's no null space. Okay, so if A is full rank, then you get positive definite, not positive semi-definite. It's semi-definite because A may have a null space, and so when you go A times X, it's possible you get 0, even if X itself wasn't 0. Okay, in which case you now get a metric of 0 when it wasn't. Okay. This leads us to what is called the spectral theorem. So let A be an n by n symmetric matrix. In that case, there exists an orthonormal basis of the corresponding vector space V consisting of eigenvectors of A, and each eigenvalue is real. The main important bit about this is that the eigenvalues are real. Okay? There's never going to be an eigendecomposition of a symmetric matrix that doesn't have real eigenvalues. This is huge for us because as data scientists, one of the most common structures we ever deal with is a correlation matrix or a covariance matrix. Covariance matrices are symmetric. This means that things like PCA will work. And you can just rely on this spectral theorem to know that you're always going to get real eigenvalues coming out of a PCA. Okay, you know that you're going to get as many eigenvalues as there exist in the data set. You're going to get the rank of the data set out. So a direct implication of the spectral theorem is that the eigendecomposition of a symmetric matrix A exists with real eigenvalues, and that we can find an orthonormal basis of eigenvectors, so that if A is doing that eigendecomposition where D is diagonal, the columns of P contain the eigenvectors. So in other words, you can eigendecompose A and then get an orthogonal basis, an orthonormal basis out of the eigenvectors. Again, that is the foundation of principal components analysis. Okay, so consider this example. If you take the characteristic polynomial, you get to this point here. What is the algebraic multiplicity of 7 in this case? It's on the slide. Do you guys just not like speaking to me? Well,
It's a great one. Let's see as 1.
Okay, cool. Why?
Because 7 only appears as 1. So
Correct. What is algebraic multiplicity of 1? Correct. Why? Because it's squared, right? Is it just because you wrote a test there? Like, are we just tired? Or is this not, no, genuinely, I'm asking, is this not making sense now? Or is it just because we're a little bit tired, we don't feel like chatting? Guys in the back? What does thumbs up mean? Makes sense, okay. All right, please do tell me if it doesn't. I'll go as slow as we need, all right? So in this case, then you can follow the standard procedure, and actually at the end of this lecture, we won't get to today, I have an example of solving eigendecomposition. So you all see kind of a very clear example of how to just do that. So following the standard procedure, though, you can obtain the following eigenspaces. So E1, the eigenspace which spans your first eigenvectors or the eigenvectors associated to value 1. And then E7 is your eigenspace for eigenvalue 1. You guys know the question, what's the geometric multiplicity of E7? Correct. What's the geometric multiplicity of 1? Not 3. The algebraic multiplicity was only 2. So lambda only appears twice. So we know that it can't be larger than the algebraic multiplicity. Yes.
Okay, saying lambda minus 1 squared.
Yes. So when you solve the characteristic polynomial, so to do that, you take the determinant of a minus I, right? When you solve that, you get this term over here, right? And again, there's an example of doing the computation, but let's just get the idea.
Lambda is into 0.
So you set your characteristic polynomial to 0. That's correct. Yes. So now in that case, what values of lambda give you a 0 on the left-hand side? Lambda equal to 7 would give me a 0, right? And then similarly, lambda equal to 1 would give me a 0. Correct? Okay, but that has a power of 2 there. So essentially, there are 2 terms. You know, we can FOIL this out and go lambda minus 1, lambda minus 1, lambda minus 7. negative equals to 0. How many times does lambda equal to 1 give me a 0? It's that term and that term. Okay, so algebraic multiplicity 2, and then I come here and I have two eigenvectors, two different eigenvectors associated to that eigenvalue. So how? Yes.
Like 3 eigenvalues.
You do?
We do, but we don't have to like write it so that this is the first one. Then let's say lambda 1 is the first one, lambda 2 is the first one also. Then lambda 3 is gonna be 7.
Okay, so typically you write it as like, yeah, yes. So what you would just do is go lambda 1 is equal to 1 and then lambda 2 is equal to 7, because that's not unique, right? But when you solve it, you would put it in, it would be 1, 1, 7, right? So that you would still create you need to keep that many dimensions in that matrix, that diagonal matrix. So that would be D then. But when you're writing it out, you just need to say what the eigenvalues are. And then in the actual question, I ask you to give the full decomposition so that I can check that you write it properly. Okay. All right. So in that case, how many you have two vectors, eigenvectors associated to the eigenvalue 1. What is the geometric multiplicity? Correct. Thank you. All right. In this case, we know that E1 and E7 are going to be orthogonal. However, these two vectors here, x1 and x2, are not necessarily orthogonal. So only when they have distinct eigenvalues do we know that the eigenvectors are going to be 90 degrees to each other. What's up?
E1 and I guess E7 are orthogonal because they don't share any similar eigenvectors.
Values. Yes. They will obviously have different eigenvectors to be orthogonal, but you know that because they have a different eigenvalue.
And so because like the eigenvalue of E1 is 1 and that's times 2, we don't know that those are orthogonal, but we know since that's obviously for 1 and 7, we know those are.
Yes, correct. Okay, so in this case now, that basis for E1 is not necessarily an orthonormal basis. So to remind us what we're up to here, we're saying that we can always, when we have a spectral theorem, when we have a symmetric metric, we can always write it as an orthonormal basis, okay? But we just showed now that we don't get an orthonormal basis by default out of the symmetric matrix. So what do we have to do? Well, let's first prove that it's going to be possible. So now we need to form an orthonormal basis from x1, x2, and x3, while the new basis vectors must still be valid eigenvectors, all right? So we can't make them not eigenvectors. Okay, so observe that since x1 and x2 are eigenvectors associated with the same eigenvalue lambda, it follows that any linear combination of them will also be eigenvectors. Okay, you just need to find that space. Okay, so for example, alpha times by x1 plus beta times by x2. So a linear combination of those two eigenvectors. If I am multiplying them both by a, that should then give me, that's kind of how we extract an eigenvector, right? So if I multiply that by a, I can distribute out, and then we know that a times by x1 gives me the lambda times x1. That's the definition of the eigenvalue, right? So I'm going to substitute that in on both, and we know that's going to be the same eigenvalue lambda. In which case, then we can regroup the terms, and we get lambda up front. And so what we've written is that same definition of an eigenvector for A, but now as a linear combination of x1 and x2. Okay? And you had to go through the steps of foiling it out. We had to go through the steps of saying, well, if I have this linear combination of my eigenvectors multiplied by A, does that still give me does that still fit the eigenvalue definition? And is the eigenvalue different? That's the whole point, is that this lambda out front is the same lambda as was valid for x1 and x2 separately. Okay? That's the crux of the proof. If that was a different thing, then this wouldn't work, because now you'd be getting a new eigenvalue. Okay, so the whole point of this proof is to show that when you take a linear combination of your eigenvectors, you get the same eigenvalue out when you multiply it by a. Okay, so any linear combination of them is an eigenvector, and so this allows us to use the Gram-Schmidt orthogonalization method safely to find eigenvectors associated to lambda 1. Okay, you can just Gram-Schmidt your eigenvectors. All right. So specifically, you come through and you set x1, your new x1, to be equal to normal x1, because that's the definition. and then you take x2 minus the component of x2 that lies on the span of x1. Again, you should probably know Graham-Schmidt at this point. Okay, use this definition. Again, I don't love this definition because it gives us a matrix. I much prefer to do that bit first, but up to you. Ultimately, what you end up getting is a new x2 over there. Okay, so then you can ask, well, if I've now changed x1 and x2, fair enough, it's still kind of lying in the same space and it's going to be a linear combination of my two vectors, but is it still going to be orthogonal? And the answer is yes. In that case, it's always going to be true because, again, it's constructed from vectors that were originally orthogonal to x3. Okay, so there's no manipulation I can do just using those vectors that is now going to put me back into the higher dimensional space. Okay, in other words, x3 sits in the null space of x1 and x2. It's the parts that it can't reach. Okay. Okay, I'm going to run through the determinants and the trace and stuff like that, and then we can wrap up for today. So one of the benefits of eigendecomposition is that if we want the determinant, it's just the product of our eigenvalues. We saw it in our earlier examples, kind of you just take the how much of a stretch is being combined in all of the dimensions. But it's important that you take the product because it's the area that's being stretched, or the volume. It's multiplicative. If I stretch in two different directions, then it's going to be 2 times 2 is the amount of area that has changed. All right? So that's the determinant of the product. The trace, on the other hand, again, I'm still kind of seeking that very geometric interpretation of the trace, but fortunately, the trace is the sum of your eigenvalues. All right, and this falls out. It's something that I was kind of hoping to get to today, but we'll save it for when it's the right time. This falls out of that idea that your trace can be calculated on equivalent transformations, right? So we've said what our equivalent transformations are in the past. I think it's that way. All right, we've said that A and D in this case are similar transformations, and so you can take the trace on both of these, it would work, okay? And so where we're heading with this is that ultimately eigendecomposition is just a change of basis, all right? Such that now you're working in a more interpretable basis, but still providing the same operation, all right? That you're still, when you multiply by your eigenvalues, performing the same or a similar operation. Anyway, we will come to this fact. Let's leave it at Kolesky decomposition for today. Oh, okay. Well, I can just show you the. So if I'm applying mapping A, right? What I can also do is go. So I'm taking A times X. What you can also do is decompose it into the eigendecomposition, which is that up there, right? And so ultimately it's PD P inverse X. Okay, this is a change of basis. This is a change of basis. And then D is a similar mapping. It does the same thing as what A does, just A is working in my original basis, whereas D is working in my new basis. And so in eigendecomposition, it's pretty intuitive. The mapping by P is just a rotation. Okay, I don't love the fact that they use E1 and E2 here because that's the canonical basis. But anyway, ultimately what you're doing is you're starting in this canonical basis, you're rotating to axis align yourself such that you are now just going to work along P1 and P2. All you can do is stretch those directions. So you stretch P1 and P2, and then you rotate back. You rotate back into the original space that you were in. And so every manipulation or every product by a square matrix A can be represented as a rotation, then a scaling, then a rotation back. The one important thing to note, though, is if you remember our notation of a change of basis, right? You have your forward transform is B times by F gets you to B hat. But we're working on coordinates, so you do the opposite, right? So if you want to work on coordinates, you're operating on this side. Okay? So ultimately, if we wanted to transform to our eigenbasis, okay? So we wanted to go from our canonical, our diagonal basis. If we wanted to take our system into my eigenbasis, the basis defined by my eigenvectors, that's just the forward transform. Okay? That's the forward mapping. But in this case, B is an identity. So B hat, my new basis, is just, or my forward transform is just the new basis I want to move into. Okay, and that's the key thing about eigendecomposition. It assumes your original basis is canonical. So B will always be identity in that case, so that you know that your forward transform onto an eigenbasis is just by multiplying by those vectors themselves. But that's if you want to transform onto the basis. But we're dealing with the coordinates. So we know that then you do the opposite transform on the coordinates, right? I'm transforming onto my eigenbasis, so my coordinate's going to move in the opposite way. And as a result, I have to multiply coordinates by F inverse, which is why we multiply by P inverse first. Multiplying the coordinate by P inverse is the same as transforming the system onto my eigenbasis. Once you're in your eigenbasis, you now perform the similar transformation to A, which is D, and we know that D is diagonal. And that is why the eigenbasis is so important, is because it gives you the same system. It gives you the equivalent or a similar transformation that is diagonal. It takes one complicated n-dimensional system and turns it into n one-dimensional systems. And so you can do things like integrate, you can solve your differential equations, you can take the product of a matrix. That's why it matters, okay? But if ever it's unintuitive of why P inverse, why it's P inverse first, because that was always a thing when I was doing this. I was like, why P inverse first? That makes no sense. It's because when you change your basis, you do the opposite direction on your coordinate. Opposite being P inverse. You've now mapped onto P as your basis. Then you do the same thing, and then you do your backwards transformation, which is times by P. Okay, I'll go through that again if that didn't land for anyone, but that's the kind of whole crux of it, why I think this is such an important concept, and why I think you need to understand basis and going forward and backwards to understand it properly. Cool. All right. Hope that was useful. Thank you for sticking around after your test. So I don't lecture nobody, and I'll see you guys in a couple of weeks.